Basically, our work is about film cooling in gas turbine blade. This work deals with two main parts, technical part and CFD part. In the first part, film cooling has been improved by using an innovative cooling technique. In the second part, the powerful tool, large eddy simulation, has been used to predict the film cooling performance. So, this paper also takes into account the large eddy simulation requirements such as grid size and time step. Now I will start my talk with the paper titled Heat Transfer Enhancement Using an Innovative Film Cooling Design, and of course, as I mentioned earlier, by using the large eddy simulation method. First of all, we need to know what is film cooling. In film cooling, the coolant is injected into the high temperature mainstream boundary layer from a series of holes or slots drilled at several locations along the exterior surface of the blade as shown in the figure. Once injected into the hot mainstream, the coolant creates a protective blanket between the hot mainstream gas and the turbine components. This insulates the outside surface of the blade from the hot combustion gases, further reducing heat transfer. This thin layer consequently acts as a buffer to maintain a lower temperature on the surface. With the aid of the film cooling technique, higher turbine inlet temperature is possible, which in turn improves the power and thermal efficiency of the gas turbine engine. Therefore, film cooling is one of the most useful techniques for protecting turbine blades from thermal failure caused by operation in a high temperature environment, and effective film cooling is of critical importance to the gas turbine industry. When a coolant jet injected in a mainstream flow, it was found that the interaction between the two fluids results in the formation of highly complex counter-rotating vortex pairs near the blade surface. The mixing process is controlled by the dynamics of these vortices. They are known as the main contributor to a dramatic decrease in film cooling effectiveness because they have two undesirable impacts. Firstly, the hot gas is pushed to interpenetrate the coolant flow, thus destroying the thermal protection layer and heating the blade surface. Secondly, these vortices tend to lift the coolant jet flow off the surface and dominate the flow field far downstream of the injection hole exit. Here is the main idea of our work. We need to reduce the effect of these vortices to keep the coolant near the surface or the blade surface by using an innovative design. I will explain this design later. So why we are doing this work? There are many reasons for doing it. Enhancing the heat transfer of the film cooling with the use of the anti-vortex hose design without significant additional machining effort. Optimize a configuration of the anti-vortex hose. Investigate the impact of the anti-vortex hose design on actual gas turbine blade, and this new design will be helpful in understanding the physics phenomena regarding the film cooling and beneficial in designing more efficiently cooled turbine blades. As you can see here, the blade configuration includes the first stage stator, the first stage rotor, and the second stage stator. Also, the film hole configuration has one row of holes placed on the pressure surface of the blade. Each row has 3 standard cylindrical holes with a diameter of 4 mm. Realistic boundary condition was used at the inlet of the gas turbine in place, and repeating interfaces was used between the stators and the rotor blades different values of flowing ratio ranging from 1 to 5 was also used. Here is the new film cooling configuration. I mentioned earlier that a row of standard film hull is positioned at the pressure side of the blade, the blue color. Each main hull, I mean by main hull the standard hull or the original hull. Each main hull is supplemented with two symmetrical side hulls, the red color, which are branched out from the same main hull, so the hull system here is called the anti-vortex hulls design. In other words, the anti-vortex hulls case is exactly as the same as the blade case or the original case, but with two additional hulls. What is the advantage of this design? First, the vast improvement in film coverage without significant additional machining efforts. Second, in this design, the two side hulls are drilled into the main hull, so it doesn't increase the main hull inlet area. In this case, the same amount of coolant used in the main hull is used in the anti-vortex design, so there is no increase in the amount of coolant. Now, how this design improves the film coverage? The answer is that the anti-vortex design generates anti-counter rotating vortex pairs, which are opposite in the sense to the main counter rotating vortex pairs produced by the standard hulls. These new vortices mitigate the effects of the kidney vortices formed by the main film hulls in the downstream region, as well as reducing the coolant penetration into the hot mainstream, and forcing the coolant jet formed by the standard hulls to remain attached to the blade surface. If the coolant stays attached to the blade surface, the film coverage will of course be improved. To study the effect of the side hulls position, three different locations of the exit of the side hulls, the anti-vortex hulls, were examined in this study. Case A, upstream anti-vortex hulls, as the side hulls emerged upstream of the main hull outlet. Case B, inline anti-vortex hulls, as the side hulls merge in line with the main hull outlet. And C, downstream anti-vortex hulls, as the side hulls emerge up downstream of the main hull outlet. Here I need to move to the second part of this paper. I will shed the light on large dissemination requirement. 4 grid sizes are adopted in this study to examine the grid resolution. The total number of grids are nearly 4, 8, 13, and 17 million. The effect of the grid size on the mid-span plane and span-wise average film cooling effectiveness distribution was examined, as shown in these two figures. These two figures indicate that there is no significant change in film cooling effectiveness when the grid size is increased above 13 million. Therefore, the grid size with approximately 13 million cells was selected for computation. An additional assessment of the grid quality can be carried out by inspecting the power spectra, density of the instantaneous streamwise velocity and velocity fluctuation, calculated based on a time series consisting of 72,000 samples. The -5 to 3 to -10 to 3 slope of the spectrum in this figure confirms the suitability of the grid for the current LES, indicating that the implicit filter for LES lies within the inertial subrange close to the eddy dissipation region, which is one of the basic demands for well-resolved LES calculations. A time step of 1.39 times 10⁻⁵ seconds was chosen for the current simulation. This time step keeps the current number CFL less than 1 for most of the flow field. However, to ensure that the chosen time step was enough to capture the small scales, the larger Taylor and Kolmogorov time scales were calculated at different locations and compared with the time step size chosen for the current LES cases. This figure shows that the chosen time step for the present simulation is even smaller than that common ball of time scale, which is one of the requirements of LES method. The computational domain of the present study consists of fluid around the first stage stator, the first stage rotor blade with tip clearance, the second stage stator, and fluid inside the film holes. The computational domain was divided into two regions with different grid structures, as shown in this figure. Therefore, two multiplex grids were generated using pointwise software, one covering the 1/2 turbine stage and a second one inside the film holes. The domain of the 1/2 turbine stage was composed entirely of hexahedral meshes, which are more accurate with less numerical diffusion. This domain was divided into a near wall region and a far wall region. The second domain, on the other hand, consisted of two rows of film holes. Tetrahedral meshes were used in the film hole domain since they are flexible to construct. These two meshes were then merged together to form a hybrid meshes with a non-conformal interface boundary between them. The large eddy simulation equations in tensor notations for a three-dimensional, time-dependent, and incompressible fluid are expressed as follows: continuity equation, momentum equations, and energy equation. The STAR-CCM CFD code is used to run the simulation using the Whaley subgrid scales model to capture the small eddies of the turbulence flow, and of course with the using of finite volume approach. Here I'm going to make a comparison between the results of standard holes and the results of anti-vortex holes design for low and high plowing ratios. When looking to these figures with the same plowing ratios but with the additional anti-vortex design, a great enhancement in heat transfer can be seen compared to that of the standard hole, no anti-vortex hole, especially at high plowing ratios. By comparing the anti-vortex cases with the standard case, the film coverage improved by 50 to 60% at low plowing ratios, while it improved more than 100% at high plowing ratios. These figures show the film coverage of upstream anti-vortex case. The figures in this slide and the next three slides also show that there are obvious differences among the three anti-vortex cases at the same plowing ratio. This means that the side hole's position is an important factor in the anti-vortex film cooling performance. For the upstream anti-vortex holes case, as shown in this figure, the exit of the side holes are placed upstream of the main hole. With the rising of the plowing ratio, this case seems to indicate jet lift-off and reattachment. At plowing ratio equal 5, it shows a more monotonic decay in film coverage. The largest film coverage is at plowing ratio equal 1. The trend of this case is similar to the standard case. The coolant is also completely detached from the surface downstream, where the coolant lift-off phenomena appears at plowing ratio equal 3, and then it's reattached to the surface further downstream. This is a dramatic reduction in film coverage in the near hole region when the plowing ratio exceeds 3. There is no film coverage in the region immediately downstream at plowing ratio equal 5. For the inline anti-vortex holes case, the exit of the side holes are placed in line with the main hole as shown in this figure. There is no coolant lift-off even at very high plowing ratios. As the plowing ratio increases, the span-wise and downstream film coverages increase and cover a bigger area. This case provides greater coolant protection on the blade surface as compared to the standard and upper anti-vortex cases and it is visible that the highest effectiveness occurs at blowing ratio equal 5. In this case, the exit of the side holes are very close to the main hole, so the coolant jet interactions from the two side holes are very prominent. The coolants from the two side holes interact between the main hole and generate another jet streak similar to the main coolant jet. Further downstream of the film holes, the jet streak of the side holes mixes with that from the main hole and thus creates a thicker coolant streaks footprint than that from the other cases. The footprint of the coolant can be recognized in the near hole region. For the downstream anti-vortex holes case, the exit of the side holes are placed downstream of the main hole as shown in this figure. The trend of this case looks similar to that of the L-line case for different values of blowing ratios. To further illustrate the mechanism for enhancing the heat transfer of film holes using the anti-vortex design, the temperature contours at the mid-span plane for the standard and L-line anti-vortex hole cases at 3 different blowing ratios are shown in this figure. For low blowing ratio of 1, the jet penetrates smoothly into the hot mainstream and then it immediately fully attached to the blade surface for both the base and L-line cases as shown in figure A. With increasing the blowing ratio, the jet tends to detach from the surface downstream of the film hole and the hot mainstream flow is penetrated underneath the jet for the base case as shown in figure B. For the L-line case, the coolant jet stays attached to the blade surface. A similar trend of the temperature contours results can be clearly seen in figure C, where the jet lift-off effect will become magnified. This figure presents the effect of side holes position on the span-wise average film cooling effectiveness for two blowing ratios. I didn't put results for blowing ratios between 2 and 5 because they have the similar trend. The case of film cooling effectiveness is similar to that of the film coverage. This figure shows that there is a significant enhancement in film cooling effectiveness of both the L-line and downstream cases compared with that of the base case and upstream case at all blowing ratios, especially at high blowing ratios. These two figures present the temperature distributions on planes normal to the blade surface. For the base case, as I mentioned earlier, the well-known kidney vortex pair produced by the interaction between the hot mainstream flow and the coolant flow can be seen developing downstream of the film hole, where the coolant jet is strong enough to keep the vortex shape well at this distance. The counter-rotating vortex pair strength is strongly affected by the blowing ratio. As the blowing ratio increases, the counter-rotating vortex pair vortices lift the coolant off the surface, which causes a rapid decrease in film coverage. The new anti-counter-rotating vortex pair vortices produced by the new design try to move against the main hole vortices because they are rotating in the opposite direction to the main vortices, keeping the coolant flow near the blade surface. This phenomena can strongly improve the film coverage and effectiveness. The main conclusions of the present study are that the results show that the innovative design of the anti-vortex holes significantly enhances the heat transfer immediately downstream of the film holes compared to the baseline case, the standard one, especially at high blowing ratio. The side holes position, upstream, L-line, and downstream cases have a significant influence on the anti-vortex design film cooling performance. For the base case, the Spain average film cooling effectiveness probably drops in the near pole region as the blowing ratio increases. Finally, the inline and downstream anti-vortex poles cases have a great film cooling performance at blowing ratios ranging from 1 to 5, and this is the important conclusion in this study. Thank you very much for your listening.